In this problem, we're not given the frequencies, but instead we're given the beat frequency. So we know that beat frequency is basically the difference between two frequencies. Now let's denote that as delta F, which is 4.5 hertz. And since the other objects, or since the other automobile is moving towards the other one, so that means the observed frequency will be higher than the source frequency, right? So we can write that down as this. So source frequency is lower than the observed frequency, and that's lowered by the beat frequency. So as we mentioned, that beat frequency is nothing but the difference between the source and the observer. So that's the tricky part. We need to understand which one is higher and which one is lower. Now we use this equation. This is from equation 12 2a to find out the source frequency. Now if we write this equation in terms of source and observer, we get something like this. So we have F observed, which is equal to F source divided by 1 minus velocity source over speed of sound. Now for our case, we're assuming 20 degrees Celsius, so that's why the speed of sound wave will be 343 meters per second. So we'll be using that. But anyway, so now we see we have two equations, and we need to solve for F source. So if we get rid of this uh, F observed on both sides of this equation, we get something like the following. So we'll have F source plus delta F, which is equal to F source divided by 1 minus velocity source over velocity speed of sound. Now if we take F source on one side and put the other terms on the other side, we get delta F times velocity speed of sound wave over velocity of the source minus 1. And then we know that delta F is 4.5 hertz. As we mentioned, speed of sound is 343 meters per second, and the velocity of the source is 18 meters per second, and we subtract 1 from there, and after doing the math, we get 81.25 hertz. So that's the frequency of the source. Thank you.